In today's video, we shall be discussing about projection operators and a bit about commutator algebra in quantum mechanics. To start with, the projection operator. Now, an operator P is said to be a projection operator if it is Hermitian and equal to its own square. Now, we know about the Hermitian operator that we discussed in the previous video. So if the adjoint of the P is equal to itself, then that is a Hermitian operator. So this is the first condition, with the second one being that if the square of P is equal to itself, then it will be a projection operator. That is, it is Hermitian in the first place over here, and then we have the square of it to be equal to itself. For example, we have the unit operator to be a projection operator where a unit operator is equal to its adjoint as well as the square of the unit operator is equal to itself. So this is an example of a projection operator, which is the unit operator. Now there are some properties of projection operator, the first being that the product of two commuting projection operators, let us say P1 and we have P2, they are two commuting projection operators, then the product of that is also a projection operator, because we have these are two commuting projection operators, and if we go on to see the product, then we have P1, P2, and we take the adjoint of it. Now, because in case of taking the adjoint of the product, we will be changing the order while we open the braces over there. So opening the braces or the brackets, we have P1, P2 to become P2, P1 adjoint, and then we have the adjoints to be equal to themselves, that is P2 and P1, and that is nothing but equal to P1, P2, because they are commuting. So, and also the case that P1, so in this case what we see is that the product over here, the adjoint of it is giving me the same product back. So that means that satisfies the first condition of it being the Hermitian part. And also the case where we are taking P1, P2 squared, the product, the square of the product, then that will result in P1, P2 followed by another P1, P2, and that will be equal to P1 squared, P2 squared. Now since they are individually projection operators, so we have P1, P2 back again, that is the product. So the square over here is equal to the product, the square of the product, or the product squared is equal to the product itself. So the product of two commuting projection operators is also a projection operator. So P1, P2 is also a projection operator. Now, considering the next property, we have the sum of two projection operators is not generally a projection operator. So if we have two projection operators, the sum of two projection operators is not a projection operator. Now, however, if we wish that the sum was a projection operator, now let's say we have P1, P2, and it continues P3 and so on. If we wish that the sum is a projection operator, if the sum is a projection operator, then we must have, it is necessary and sufficient that these projection operators be mutually orthogonal. These projection operators, it's a necessary and sufficient condition that these projection operators be mutually orthogonal, which also tells us that their cross product or the outer product must vanish. We can see a case related to that. We'll have an operator. Let us say we have the outer product of two state vectors with the same state vector, that is, and supposedly it is normalized. So we have the outer product over here, which represents an operator, is supposedly a projection operator, and we have this will be a projection operator only when this state vector is normalized. Let's see how. Well, if we are taking the square of it, now as far as the case of taking the adjoint is concerned, we take the adjoint of it first, and taking the adjoint won't really make a difference because you have them to be shifting on either side and they result for the same thing. Now let's look at the square case where we are taking the square of this, and taking the square of it we end up with this, that is psi. This is the ket vector first, followed by the bra vector. This is 1, this is another one, will be just a copy of it, and then if we open those braces over there, what we get is this is psi ket, and we have the inner product over here followed by the bracket, the bra psi. And because it is normalized, as you can see, this will go to 1, and what we are left with is the same operator, suggesting that this is projection. First we had the case of the adjoint being equal to itself, and then we have the square being resulting the same thing, that is the projection operator itself. So the case here to consider is that it has to be normalized first, then only can we have the projection operator, and also we have these projection operators to be mutually orthogonal, then only the sum of the projection operators is going to be equal to a projection operator. We already have the product to be a projection operator, but also the case where we if we have the two projection operators, not necessarily they can be resulting, their sum is not necessarily a projection operator, which was the second property that we studied. The third property tells us how they can be made to be a projection operator, that is the sum. Now, two projection operators are said to be orthogonal if their product is 0. This is we know this for sure, that two projection operators will be orthogonal if their product is 0. Now we shall discuss about the commutator algebra. Now the commutator of two operators, supposedly A and B, is usually represented as A comma B within those square brackets, and that is equal to the product AB minus BA. It's pretty straightforward. And then this is minus, and then if we are to consider the anti-commutator, then we have this as the commutator, and the anti-commutator is having them in the curly braces, and that is equal to the sum of the product of A and B followed by A and B with BA. So this is the anti-commutator. Now the two operators are set to commute if their commutator is equal to 0. So they are commuting if we have A, B to be equal to 0. So then we also have the condition that this is equal to 0, the right hand side is equal to 0, which means the product AB will be equal to BA. So then we'll have them as commuting operators. Now any operator commutes with itself for sure. So this is for the case of the self commutation. Now if two operators are Hermitian and their product is also Hermitian, these operators will definitely commute because we have AB, the adjoint of it, to be equal to BA, and that is equal to simply BA because they are Hermitian. So we have AB adjoint to be equal to BA. Now since AB adjoint, because they are Hermitian, so this will be equal to AB itself. So we have AB to be equal to BA, and that is the condition for the operators commuting with one another, or they commute, and their adjoints or the Hermitian operators, they will definitely commute. As an example, we may mention the commutators involving the position operator and the x component of the momentum operator. They have the following cases. Suppose we have the position operator as x, and we have px. Now, as we know that px is simply equal to minus I h bar del over del x. So using that case, we have this to be equal to I h bar I operator, which is the unit operator in this case. Similar will be the case in the other components, that is, for supposedly we take y and the y component of the momentum, and we take z and the z component of the momentum. All are going to result in the same thing, that is I h cross with the unit operator. The properties of commutators can be laid down as follows. The properties being, the first one being the case of antisymmetry. They are antisymmetric because we have AB to be equal to minus BA. Then we have the case of linearity. Linearity suggests that we have A, and that is, suppose we are taking the commutator with the sum of the other operators that are there, then this will result in the commutator relation as follows. You can think of it as distributive, but it's not, because distributive usually relates with the product terms, and it follows like that. And the Hermite conjugate of a commutator is like this, that is, if we are taking not the Hermite but the Hermitian conjugate that you see is like this, which is B adjoint A adjoint. This is the Hermitian conjugate. Then next we have the distributivity. Now we can consider the case of products, that is A, B, C will be equal to A commuting with or the commutator of AB followed by product with C, then that is added to B multiplied to the commutation of AC. Then again, if we have the other way around, that is AB, and we have the C operator, they're commutating with the commuter of AB with C, then we have A followed by the commutator of BC, then we have AC, the commutator of AC multiplied or multiplied uh, to the operator B. We can also have the Jacobi identity. The Jacobi identity suggests that we have A commuting or the commutator of A with the commutator of BC plus the commutator of B with the commutator of CA. You must take care of the order in that case. As you may notice, it is cyclic and we are taking the sum over here. Then we take the commutator of C with the commutator of AB, and all that adds up to 0. So this is the Jacobi identity. We can consider this distributive property that we have learnt over here, and we may come up with another property where we have the power term involved. So the commutator of A with B raised to the power n is going to give me the summation taken over. Supposedly we take an index j which is taken from 0 to a value n minus 1, where n is obviously the power term or the power of B. So we take it to n minus 1, and we have that index in the power of B. So B operator raised to the power j multiplied to the commutator of AB, and then we have again B raised to the power n minus j minus 1. Conversely, if we have A raised to the power n with B, then is the other way around. We take the summation in the same manner, that is from 0 to n minus 1. Here we'll be taking A n minus j minus 1, following it with the commutator of AB, and then we have A raised to the power j. So if you look at it, the ordering is just reversed. In this case, the term which was on the right above is now on the left, but obviously in that case it was B. In the at the bottom you have A. So this is just a replacement of sorts. And let me squeeze in another property over here, probably the last one, which is that in case of scalars, suppose we are taking the commutator of an operator with a scalar, that is obviously going to result in 0. That means the operator always commutes with a scalar quantity. B here is a scalar, any scalar. It's not necessarily any particular one, it can be any scalar. Now, having learnt all of that, here are a few cases that we can consider. We can squeeze in a few cases over here. That is, if we are having two Hermitian operators and we are taking the commutator of two Hermitian operators, so the commutator of two Hermitian operators is anti-Hermitian. Let's see. Well, if we have supposedly two operators, let us say A and B, and they are Hermitian, which means their adjoint is going to be equal to themselves. So there's no issues with that because we have considered that. Now, if we are taking the commutator of these two, and this is the commutator of two Hermitian operators, and suppose we take the adjoint of it now, then we have now this adjoint is obviously going to give us a b for sure because they are Hermitian, so there's no problem with that. But if we look at it this way, no, it's not going to give us that value because a and b individually are Hermitian. So a adjoint is equal to a and b adjoint is equal to b. So that's provided over here. Let's look at this commutator relation. So we have AB minus BA all within that adjoint mark, and if we open that, then we have the adjoint of B multiplied to the adjoint of A, that reverses in order. And similarly in the second case also we have A and B in reverse order with their adjoints taken. Now because they are Hermitian, so we have BA over here minus AB over here. As you can see, this is just the negative of AB, the commutator of AB. So we have the commutator of AB to be an anti-Hermitian, which is the case that I have mentioned over here. Now, if we consider the distributive relation, we can also prove that A, B, C, where we take the commutator of BC, then we take and we multiply a D to it, then this entire commutator, the commutator of this entire thing, can be evaluated. So let us evaluate by using the distributive property. Now here we can first of all have BC multiplied to the commutator of AD plus A BC D. We treat D as the extra term and then we use it. So this ABC is taken as 1 in the first case, and we take the D as the separate case, and we do it just like we did it in those 3 cases of ABC. So here we have BC minus CB, then that is multiplied to AD minus DA. Then over here what we do is we keep A as such, and we have BC minus CB, and we can take the D inside, and then with that commutation relation we had first put A times of this entire term. Now we can take that entire term BC minus CB and put the A in the second place, considering this commutation relation over here, and that is multiplied to D over there. So if we open the braces now, we have BCAD minus CBAD minus BCDA plus CBDA. Now CBAD was there, CBDA is here. Let's see what we can get. If we can cancel out a few terms, we'll see to that. Then we have for the second case minus, no, this is plus. So plus ABCD minus ACBD minus BCAD plus CBAD. Let's see what we are cancelling out. We are cancelling out this with this. Then is there anything else that we may cancel out? We have BCDA over there. Is it repeating? No. We have CBDA. Well, we have BCAD to be cancelling out with BCAD. And then is there anything else that is cancelling out? We are left with just 4 terms now. So we write the pluses first and the negatives after that. So we have ABCD plus CBDA minus BCDA minus ACBD. So here's an example of how to use the case of distributive property we had provided 3. Now we have tried it with 4 operators. You can try a few more of those and practice them so that you get to know how they are done or how they are evaluated. In case you were confused with it, then I can provide you with another way of doing it. Another way means I will be doing it in the same way, of course. This is what we had obtained in the distributive property. Now the B and the C's may be confusing. We can take this term as simply as M. Okay, so this is AMD now. Now instead of BC over here, I take it as AMD, which is the case in the above question. So the second term is what I have written in the first place, that is M instead of B over there, M A D. You can see that is BC is M, so this is M A D. Then this is AMD, because here is AMD. So this is how I started off, and then I opened the braces over here, the square brackets. The commutator relation was expanded, and then we had the result that was at hand. So you can simplify all sorts of things by considering as they should be done. So this was it from this video on operators. We'll be dealing with a few more to follow it up with uncertainty relation between 2 operators in the next video, then many more to come. Till then, thank you for watching.